Okay, so in today's lecture, we will talk about scattering from scattering of waves from periodic materials. So uh, it'll turn out we're looking at how waves behave in periodic materials is extremely important for many applications. Certainly within this course, we talk about pattern materials, and quite often those patterns, almost all the time, those patterns have periodicity. And it turns out where the periodicity, the fact that various elements, whether they're an array of resonators or split ring resonators or metallic features, the periodicity itself can cause very interesting and also useful optical phenomena. And so that's why we need to talk about it a good amount today, and we're going to devote a whole lecture to some fundamentals of scattering of waves in periodic materials so that we can sort of understand the language that we'll be using for many of the other lectures, as well as the math and some of the defined terms that we'll also be using, but then also understanding some physics that the periodicity of a material allows. All right, and to gain an understanding and start to be comfortable with that, and being able to identify the effects of periodicity when we see it in the structures we'll be looking at throughout the remainder of this course. So like I said here, in this course we will see that a lot of interesting and useful optical phenomena occur because of the scattering of waves from periodic materials. These materials can be, all right, so many of the pattern materials. Optical gratings is a very simple example, and we will look at that, far field diffraction, Fraunhofer diffraction in this section, but it really, that optical phenomenon of diffraction, far field diffraction, is due entirely to the periodicity of a structure on a substrate. And so we'll look at that. Also in this course, we'll be looking at photonic crystals. And photonic crystals essentially are an array of optical resonators, dielectric resonators. And so this, what we'll do today is absolutely essential to the treatment of photonic crystals. Also regular crystals, things that you would typically consider crystals, silicon, diamond, gallium nitride, zinc sulfide, all those different materials. If you look at their makeup using a transmission electron microscope, you see that the various silicon atoms for silicon, various carbon atoms in diamond, they are arrayed in a very regular array with a certain distance from silicon atom to silicon atom and a certain orientation, a lattice as it's called. So, so crystals themselves have regularity, and when we say going forward something is a crystal, essentially we mean that. We mean that it's a periodic array of something. That something in crystal terminology is called the basis. And the configuration of the array, how one thing is separated from the other scattering item, is called the lattice. And we'll get both into that later. Basically, a crystal is the lattice, the configuration, and what's at the various lattice points, the basis. So, so whether that is metallic lines and optical gratings, or dielectric resonators and photonic crystals, or silicon atoms in regular crystals. But then, of course, periodic patterning of any sort requires us to know the language of crystals, lattice, basis, and the variety of other things we'll talk about in this lecture. So let's look at a simple example, the optical grating. This is the simplest example of periodicity But it allows for us to build up our library of terms and physical concepts associated with this topic. So in this example, we will be examining basic scattering requirements, but we will not be looking at the details of the scattering efficiency. So we're looking at a higher level for phenomenon that occurs entirely due to the periodicity. And we won't dig into details of how well a particular scatter scatters a wave. We just assume that it does. And that's all we really need for now. And we'll get into more of the details in a later lecture. But we have more than enough to do with a higher level treatment of wave scattering off periodic materials. So that's perfectly fine, and that's what we need right now. So let's consider an array of scatters as shown on the next page. I'll bring it up here in a moment. And then we have an incident beam that impinges upon the array with an angle of incidence we denote as theta I. And it has a particular wavelength, lambda I, or just lambda. Okay, here we bring it up right here. So we assume that the scatters scatter light isotropically, meaning that when the light comes down, it hits each one of these scatters, and then this scatter will generate a scattered wave that is isotropic, meaning equal in all directions. All right. Now we can sort of drop that. We certainly can drop that assumption later on, and it won't cause any of the physical effects we will develop now to be wrong. But it's just something useful to employ right now so that we don't get into a lot of mathematical complexities that mask the very interesting physics that would be there otherwise, whether or not we do invoke this assumption or not. All right? So just take this for what it is. Believe it for the moment. It doesn't, by dropping it, like I said, nothing we would do now in the next 30 minutes will be wrong. And so it's perfectly fine. So what we will do, we will study the amplitude of a total outgoing scattered wave that is built up by the individual scattered components. So what we have is we have the incoming light coming in, and it generates an optical field, an optical wave that's isotropic, a spherical wave. Going outwards from each scatter, all right? From each scatter. And that's what these circular lines represent, all right? And then the total scattered wave is just the linear superposition. And that's something you know from electromagnetism, as you learned in the first lecture, that electric and magnetic fields obey the law of superposition. So to find the total field, this total scattered field, you would just sum up all of the scatter wave components from each one of the scatters. All right, so that's what we'll do. To simplify things, at first, let us just look at two scatters, not infinite array along this lateral direction, but only one and two, only one scatter and two scatters. All right. Now, so we only look at two scatters. And we're going to first look at what happens with the incident beam, all right? So the incident beam is coming along with this direction, impinging down and onto these scatters. It's a plane wave with a wave vector k sub I. It has an angle of incidence of theta I relative to the normal, all right? So this plane wave with constants of phase on these planes that are impinging onto this surface, this plane wave, so if we follow a particular phase point on this wave, we see that it first will encounter resonator 1. And then the same position, that same plane of constant phase needs to go further before it hits resonator 2. And we can do the geometry. This is the angle of incidence. That angle equals this one right here. This is equal to the period. Capital lambda is a Greek letter often reserved for the period or the lattice constant, the repeat unit of our structure, our gradient in this case. Then this is simply capital lambda times sine theta I. So this is not wavelength, this is not lowercase lambda. This is the period, the spacing from wire to wire. So that is, so this wave has to go an additional capital lambda times sine of theta I before it reaches scatterer number 2. So d sub I is the extra distance the beam has to travel to get to scatterer 2 relative to the distance that beam traveled to get to scatterer 1. All right, so that is the incident wave. Now, check the recording, good. Now let's look at the scattered beams. So now we isolate out the scattered beam, K sub S, coming out, all right? And so we then now look at this component of the spherical wave coming out, the component with a plane wave with K sub S, and we look at the same component that's coming out of scatterer number 2. All right. Well, this is a plane wave as well. When you start summing all these things up, the spherical waves, it'll represent a plane wave. And that plane wave will have a wave vector of K sub S. And so then you'll have planes perpendicular to the direction of propagation given by K sub S. You'll have planes of constant phase. So this right here is a plane of constant phase. So basically, this scattered wave has to go this whole extra distance before it catches up, it catches up to the plane wave component being emitted by scatterer 2. So this is an extra distance the EM field has to travel to get to sort of the starting position as defined by scatterer 2. So a little bit of geometry tells you that that distance there is lambda, capital lambda, sine theta s, where theta s is the angle of scattering relative to the normal. All right? So the wave from scatterer 1 has to travel this additional amount. Okay? So now to find the total we now construct the total amplitude of the scattered wave. All right, the total wave amplitude of the scattered beam will be equal to an amplitude factor times the plane wave, and so that will represent plane wave 1 coming out. All right, and it has an amplitude A, and then the typical e to the I ks dot r. Perfectly fine. That's a plane wave. Where we have an e to the minus I omega time dependence. Scatterer 2, you add that in there for the amplitude, and that's b e to the I ks dot r plus a change in phase. All right. All right. So we're going to work with this. What is A? What is B? What is this change in phase? Well, first of all, we can get rid of A and B quite easily. Not get rid of it, but we can say some information about it because we are assuming identical scatters, things that scatter with the exact same efficiency and are identical scatters, period. So the coefficients A and B are equal because each scatter is identical. So we just replace B with A because each coefficient out here in front is equal. All right. However, this wave number 2, when it matches up right here, it will have traveled a different distance. So when you look at the amount of extra distance the incoming wave had to travel, but also to get to scatterer 2 relative to that taken by to get to scatterer 1, but also even though it did take longer to get to the incident wave to get to scatterer 2, it is basically ahead of scattered beam 1 after scattering. And so there you have a difference in the distance that has accumulated in the two beams. So, and that has to be taken into account right here, all right? And you take that into account, this change of phi is simply equal to ki times di minus ks times ds, all right? It would just be simply the difference in the distances, but phase is given by the wave magnitude of the wave vector times the distance. So you have to take ki, which is the magnitude of the incoming wave vector, di, minus ks ds, where ks is the magnitude of the outgoing scattered waves wave vector. All right? Okay. But now, these two k's, as it turns out, are equal. All right? And we'll eventually just call it ki, or really just k. Now, why is it equal? Because of conservation of energy. Meaning that we assume that a photon of a particular energy comes in, experiences a structure, and it exits. It is scattered, but the photon retains in some particular direction. But what doesn't change is the energy of that photon. That's called that conservation of energy. And when you have the same energy, E is equal to h mu, or E is equal to hc over lambda, you have the same lambda for the incident or for the, as you do for the scatter. So with k being equal to 2 pi over lambda times the index of refraction, that's up here, and that would be of the substrate or the superstrate. Both of these are equal to the conservation of energy. So this change in phase, this delta phi, is given by k di minus k ds. And we have the values for di and ds, and so we can plug that in. And so this is my change in phase, and that's what we'll put in right here. All right? We have those two things. So now we're going to work with this in two ways. We're going to do a very simple way that will yield the famous diffraction equation. And then we'll do a much more complex way, not much more, but a more complex way. But it is very much more general and useful for what we want to do in the rest of this class, namely look at the scattering from periodic materials. All right? So we first do something fairly simple, but limited, and then we do something general, maybe more complex, but far more powerful. So, okay, let's make sure we are still recording. Good. All right. The diffraction equation. That's what we're going to develop now. So, this change in phase needs to be an integer multiple of 2 pi such that the two beams coming out from scatterer 1 and scatterer 2, such that those two beams will constructively interfere with each other. All right, so let's go back to the equation here, this right here. If A's and B's are equal, so you can take those things out, or you can just set them to 1, all right? And then you have E of the I ks dot R. And now you want this to maximally combine with then this term, E of the I ks dot R. Now, this is from scatterer 1, this is from scatterer 2. So those two terms will be equal in magnitude if this is equal to 2 pi, 4 pi, 6 pi, or so forth, namely even multiples of pi. So that's what we will aim to achieve. We will say that's a condition such that we can have a scattered beam coming out, that this change in phase given by this right here has to be an integer multiple of pi. So m is an integer here, okay? we put in the results for k, 2 pi over lambda times n, the index of refraction. We cancel out the 2 pi's and rearrange it a bit, and we get the well-known diffraction equation of sine theta I minus sine theta s is equal to lambda over the period. Sometimes this is called d in optics books, but I prefer capital lambda over n times an integer n. And if theta is equal to 0, then we have that d sine theta is equal to m lambda over n. And so this you will probably know just from your basic physics course for normal incidence, when light is coming straight down onto the periodic structure. All right. Now this term right here, the lambda over n, that is sometimes called the effective wavelength. And so what that represents is the fact that light, when it's in a dielectric material like glass, its wavelength, its crest-to-crest distance or trough-to-trough distance is compressed according to this index of refraction term. So it's, the effective wavelength is lambda over n. So if you just have lambda effective, it's, you would have the traditional d sine theta is equal to m lambda, which is what almost every physics textbook does. But I have capital lambda as the period, so it's capital lambda times sine theta, and I keep the n outside. I explicitly state what n is in the free space lambda in the vacuum. All right. All right, but you do note, by doing that, you note the effect of n on this situation, on diffraction, that the higher n is, the smaller this value is, and you can get diffraction for larger wavelengths than you otherwise could if the wave is in a higher index material. All right, there will be some homework problems with that. So, and you can, this is applied to either the top, both the top and the bottom. So in the top you may have a different dielectric constant N1 than what you have in the bottom N2, and you would apply it to both situations, both materials. So if N2 is greater than N1, then you can, as it turns out, as you'll see by studying that equation, you can have diffracted orders occurring in the substrate and none in the superstrate. All right. So if you're looking at where your incoming wave can be scattered to, you have to look at both materials and both their substrates. You may not have diffraction in the superstrate, but you may end up having it in the substrate because the substrate generally has a higher dielectric than, say, a vacuum or air superstrate. All right? Okay. So that is the diffraction equation. All right? And we derived that only for two scatters, but we only looked at two scatters, and we noted that the phase difference between the two scatters has to be an integer multiple of 2 pi. We could have gone up to 3 scatters, 4 scatters, or so forth, and we see that the neighbor-to-neighbor difference in the phase, when you add up the different scattered components, you would have the plus c e to the I ks dot r plus a delta phi, but that would be 2 delta phi relative to this, because you would have no delta phi, 1 delta phi, 2 delta phis, 3 delta phis, and so forth for each subsequent scatter. But then you'll see that you always get this relation for the delta phi, regardless if you look at 2, 3, 4, or a million scatters. All right. So you get this whether you have 2 scatters or an infinity number of scatters. Okay. So now let's generalize this a little bit more. So let's look at the situation a bit differently. Let's first recast the equation Let's first recast the equations for scattering from two scatterers. Let's recast it a little bit to have them a little bit different, all right? Or expressed in different terms. All right, so let's look at the incident wave and the scattered wave separately, all right? And we have the two scatterers, scatter 1 and scatter 2, all right? Where we've only drawn the incident wave here, like this. So we have the ki, theta I, theta I. So the angle, we denote this angle as phi I. This is theta I, this is phi I, 90 degrees. So my sine theta I turns into cosine phi I. And likewise, we call this vector going from this scatter to this scatter, from scatter 1 to scatter 2. We call that vector R1, 2, R sub 1, 2. All right, this will be what's called the translation vector, going from this scatter to that scatter, R sub 1, 2. All right. All right, so we've done that. Now, the scattered beam, we have k sub s for the scattered beam. It has an angle of scattering of theta s. With that being 90 degrees, we have this as phi s. So your sine of theta s in our equation turned into cosine phi s in the equation. And we have the same thing for r sub 1, 2, the translation vector from scatter 1 to scatter 2. So we take our constructive interference condition, and we can recast those because our sine theta I turns into cosine phi I, and my sine theta s's turn into cosine phi s's. All right. So we have magnitude k, magnitude r, cosine of the angle between them. That's obviously a dot product. So we change these into dot products of these two vectors and these two vectors. And then we call this difference between k sub I and k sub s, k sub I minus k sub s, namely. We denote that as a capital K. This will be a very important vector. And so it's capital K, but always remember it is the difference between the incoming and outgoing wave vectors. That's what capital K is from here on out. All right. So this the required phase constructive interference condition so that the scattered waves of these two scatters constructively interfere. The requirement is that k dot r12 has to be an integer multiple of 2 pi. All right. So we've recast it in terms of dot products of two vectors. We recast the phase difference. Now what this does, this allows us to nicely go up to an infinite array of scatters, an infinite array of scatters. So, like we said before, a scattered beam will have an amplitude given simply by the linear sum of the amplitudes of all the scattered waves. All right. So we have the total wave amplitude is equal to a sub n e to the I k dot r plus the appropriate phase difference, the difference in phase between the wave for scatter 1 relative to that of scatterer n. Okay, these a sub n's, we denoted it as a sub n for generality, for completeness sake, I guess, whatever. But they're actually, since they're identical scatterers, each one of them is the same. We just denoted A, so they're all the same for all n due to the identical nature of the scatterers. And then my delta phi 1 sub n, like we did in the prior page, page 8, was equal to k dot r 1n, with r being the translation vector going from one scatter, scatter 1, to all the other scatters, to scatter n. So 1n would be scatter 1 to scatter n. For example, r12 is this right here, going from 1 to 2. But if we had scatter 3 right around here, if r13 would be going all the way over to here. All right. but we're going to have an infinity number of scatters. So we're going to let this go to a very high value or even infinity. Okay. Thus, we can pull out the A's. This part is a common term. We can pull that out, and we can then express this like this. So this portion right here is the typical plane wave with an amplitude of A. Just total typical plane wave, nothing fancy at all. But this right here is a multiplicative factor entirely due to the multiple scattering that occurs in this periodic medium. So that's interesting. So this is entirely due to that. So if this were a constant, we would just simply have a plane wave, and all possible scattered directions are possible. So light would come in, and you could have scattering from all possible different directions. All right. But as it will turn out, this imposes extraordinarily strict conditions that need to be satisfied, such that you can have a scattered wave. So without it, you can have a wave come in and it can be scattered in any direction at all. All right. But now with this term here, we will find out that not any old direction is possible for your k sub s. And remember, your capital K, as I told you to remember, is your k sub I minus k sub s. All right. So really, your k of I is set. So this is going to set a condition on capital K, which therefore gives a condition on k sub s, which is a condition on the direction, all right, of the vector. Remember, vectors have both magnitude and direction. Our magnitude is set of k sub s simply because of conservation of energy. It's set to be equal to the magnitude of the incoming wave vector, 2 pi over lambda times n. But it's the direction that is otherwise free to choose, free for the system to determine. But what we'll see here is that this right here is very stringent and determines only a handful, if any, of possible directions for the scattered wave. All right? So that's what we're going to look at in greater detail. We're going to look at this factor right here. So we take that and repeat it right here. Okay? So what does this thing look like? We're going to sum over a whole bunch of different terms that are e to the I something, k dot r, all right? Where r's are the infinite number of translation vectors going from scatter 1 to scatter 2, scatter 1 to scatter 3, scatter 1 to scatter 4, and we sum them all up, all right? All right, so depending on what values k and r are, this complex function can take on any value in the complex plane that has a modulus of 1. E to the I phi something always has a modulus of 1, but depending on its imaginary and real and imaginary parts, it can be anywhere on this circle of magnitude 1. All right? And so as we do this sum, you'll have a term that might be here, 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 here. And when you do an infinite number of these, this term, the resultant, will tend to go to the geometric center of this, namely 0. If there is no sort of pattern to this sum, all right? So for any old k here, when you do this sum, in general, almost all the time you will get 0 because of the fact that you have this, and they keep going around for infinite number. The result goes to the geometric center of this shape, and it's 0. Okay? If that were to be 0, then you would have a 0 here, and you wouldn't have any wave coming out, any scattered wave coming out. All right? So for any old k, unless you're very careful, you will have no scattered wave coming out. All right? So that's what I say right here. This will sum to be 0 unless e to the I k dot r is always a constant value. All right? Say, for example, when we go from r12, that term, the very first one, e to the I k dot r12 plus e to the I k dot r13, 14, 15. If each one of those terms has it such that they're the same, then say 1, so we have e to the I 2 pi, e to the I 4 pi, e to the I 6 pi. If that's what we have, then you're always adding 1 plus 1 plus 1 plus 1. And we will not get 0, but we will get a very large number, a non-zero number, importantly, so that we can get a wave coming out of this system, this material. Okay? And so thus, this is important, thus there will be no scattered waves unless we have k dot rn, k dot r1n is equal to 2 pi m, an integer, for all r sub 1 n's. To figure out what k values provide this, we have to look a bit at crystal physics, solid state physics. Not too much, but just enough that we learn a little bit of the terminology. All right. So again, what we will try to do in the next few pages, next sort of 5 pages, is to look at crystal physics and try to figure out when we can, for what k value, capital K value, will provide us this condition, will satisfy this condition here. All right? So, now, crystal physics. An array of identical scatterers forms a crystal. That's what a crystal is, an array of identical scatterers, or items. A crystal is defined as having 2 things, or being 2 things, having a lattice. A lattice is a mathematical array of points described by translation vectors R. All right? So the keywords here, mathematical, meaning that it's not physical. There's nothing physical to touch or feel a lattice. It is just the mathematical array of points that will be the location of our items. Silicon atoms in a silicon crystal, carbon atoms in our diamond crystal, and so forth. The lattice is the mathematical array of points that gives us the locations of those atoms. The basis is what is at those points, those lattice points. It is the silicon atoms in the silicon crystal. It's the carbon atoms in our diamond. So, crystal is simply a lattice plus a basis. Now, as it turns out, there's not a really interesting thing. I was quite intrigued when I first learned this. There's not an infinite number of possible configurations, lattices in 3-dimensional space. There's really only 14 different unique ways to order items in space. 14 different unique lattices. The most obvious one is what's called the simple cubic lattice, one where, here in fact I draw it out, where it's just simply a cube. And this cube repeats in the x, y, and z direction to infinity, and that's called a simple cubic lattice, an SC lattice. All right? There's 13 other of these lattices. These are called the Bravais lattices, very famous, and quite an interesting result. This person Bravais figuring out that there's only 14 of these things, and then describing all 14 of them. We'll look at the most common ones in the next few pages. You have the simple cubic, which then, if you want to go from one scatter to another, you just go along the x and y and z axis by integer multiples of a, the lattice constant. It's called the lattice constant. So these translation vectors R that are in this equation right here are simple for a simple cubic. It's just simply given by this, where h, k, and l in this case are integers. Now, we have the k being an integer in this, and that's unfortunate because k is also our wave vector. But in solid-state physics, k is almost always used for this translation vector notation to represent this HKL planes. They call it in solid-state physics. So unfortunately, we have to stick. We should stick with that just for tradition's sake. So k here is an integer, h is an integer, l is an integer. The a's are the lattice constants given down here, and for a simple cubic, r is very simple like that. So this has a lattice constant. The lattice constant is the scatterer to scatterer distance. So this has a lattice constant of a, and the vector is a1. So I say the ax hat is, I call that a1. The ay hat is a2, and the az hat is a3. I label these, I call these something important. This is the overall translation vector, but a1 and a2 and a3 are called primitive translation vectors. They are the shortest translation vectors, going from one scatter to another. And in 3 dimensions, you have 3 of them. One going in the x, one going in the y direction, one going in the z direction. In two-dimensional arrays, you only have 2 primitive translation vectors. All right. For the simple cubic, they're simply given by what I denoted here, or collected also as well down here. A1 is equal to ax hat, A2 is equal to ay hat, A3 is equal to az hat. The volume of this box, this will be important for calculation later on, is given by this vector equation A1 dot A2 cross A3. This is the vector volume of a parallel pipette. You can always take those 3 vectors describing this volume and do this operation, and it gives you the volume of the box. And that turns out to be a cubed. So fairly simple. So that's the simple cubic. Let's go to our second common crystal. See if our video is still going. Yes. The body-centered cubic crystal. It's basically a simple cubic crystal of lattice constant A. And I denote this as the lattice constant. And we call it, if you're a stickler, to be the conventional unit cell lattice constant. All right? A bit different than the true lattice constant. But in a lot of books, this is given by A, and they call that the lattice constant. The thing to see in this picture, this figure, is that we have an additional scatterer right in the center, right in the body center of this cell. That's why it's called body-centered cubic. We have this additional one right in the middle. All right. So as it turns out, here, the shortest primitive translation vectors, you can find them, but it would be going from this scatter to the middle one. And that's given by this vector right here, a over 2x hat, a over 2y hat, a over 2z hat. Likewise, the next unique, meaning non-parallel, translation vector, primitive translation vector, is the one going from here over to the body-centered scatter over here. And that would be a over 2 x hat, but minus a over 2 y hat, going below and then up a over 2 z hat. So it's this right here. And then likewise, you could go to the scatter down below the xy plane, and that would be a over 2 x hat plus a over 2 y hat minus a over 2 z hat. All right. So those are the primitive translation vectors going from the origin scatter to one of the body-centered ones in three of the neighboring unit cells. It's not ax hat, a y hat, a z hat, or a 1, 2, 3, respectively. Those are not the shortest translation vectors, so those are not the primitive translation vectors. It's going from here, the origin, into one of the body-centered ones. All right. If you do the operation to find the volume of that true primitive unit cell, not the conventional unit cell, but the primitive unit cell, it's a cubed over 2. All right, so that's the BCC, very important. A lot of crystals have a BCC structure. And then finally, well, we'll look at two more, the face-centered cubic and the hexagonal. The face-centered cubic is a simple cubic, but on each face you have an additional identical scatter. All right? And so here, the shortest primitive translation vectors is going from here to there, from here to there, and from there to there. So basically going from the origin scatter, the scatter at the origin, to one of the ones on the faces. All right? And if you work out the vector notation, it's the primitive translation vectors are given by this right here. And then if you find the volume, do the operation A1 dot A2 cross A3, you get this result right there. And then finally, the hexagonal is one. Gallium nitride, for example, has this. So examples of what crystals have this: silicon, diamond, gallium arsenide have a FCC lattice. Gallium nitride has a hexagonal lattice. And in this case, we have this distance be A, and so we can work out the primitive translation vectors going from the origin to a couple of the scatters on the base. And then the other translation vector, primitive translation vector, is just going from, S, going from this scatter. Oh, I didn't draw one in there. There should be one right there. Right there. And so that's S times E hat. So, and where S is the distance of one plane of atoms and the other next upper plane of atoms. All right? So now we are in a position to find the capital K's such that our outgoing scattered waves all constructively interfere, build upon each other, and make for a nice, robust wave. All right? So now we have the K dot R sub n is equal to 2 pi, and that's our constructive interference condition. All right? And we've been building up what my R sub n's are for common crystal types. Hexagonal, my R sub n's, for a simple cubic, my R sub n's are given by this. So we have HA1 plus KA2 plus LA3. And we'll have that for all of the different types of crystals. We'll have the general R's constructed by the translation vectors, primitive translation vectors that we find for each crystal, and then times integer values, HA1 plus KA2 plus LA3. Whether we have the simple cubic, the BCC, the FCC, or the hexagonal. The R's are always HA1 plus KA2 plus LA3. All right. So, but now, so since k is a vector, let's write it in terms of three different vectors as well. And we'll call these primitive translation vectors, but for a different lattice, a reciprocal lattice, a different lattice than the real space lattice describing the physical items, the silicon atoms for silicon. This is, K will be another lattice, but a different lattice, something we call the reciprocal lattice. All right? And now, but what we're shooting for is for this condition to hold. So let's guess. Let's guess what B1, B2, B3 could be such that we can get this condition to hold. Well, it might have been Bravai. I don't quite know who did this, but somebody tries this result out, or that they said, well, what if B1 is equal to this, where we use our primitive translation vectors, A1, A2, and A3, in this way to define B1, B2, and B3. All right. See, this is A2 cross A3. This is A3 cross A1. And this is A1 cross A2. So let's do this. If we were to say, okay, let's now put this in for this, this in for this, this in for this. And then that's our K, and now let's dot it into my R's, which is H, A1, plus lowercase k, A2, plus L, A3. Do that dot product. What you will find is you get 2 pi times the quantity SH plus PK plus QL. If all of these are integers, then this whole thing is an integer. So then if your k's are indeed given by these equations, you will get k dot r is always equal to 2 pi times an integer. That's what we need then. So if my k, and again, remember, capital K is equal to the incoming wave vector, lowercase k sub I, which is given, minus the outgoing wave vector, k sub s, which is what we want. And so now we figured out that k has to be of this form with the B1, B2, B3 given by these three equations, and S, P, and Q being integers. Then we get the magical constructive interference condition satisfied. That's what we see. For each lattice, the array of points defined by K define another associated lattice. All right? So we basically have been now calling this thing another lattice. It is called in solid-state physics the reciprocal lattice. All right? And I'll have you verify this, but if you take the A's for a simple cubic, the A1, A2, A3, and put it in these equations, you will find that that simple cubic lattice in real space, meaning real physical space, the lattice constant, the simple cubic lattice with the lattice constant A is associated with this another lattice that's also a simple cubic, but with the lattice constant of 2 pi over A. So you will have in our work in later sections, we'll be asked to say what's the reciprocal space lattice for a simple cubic real space lattice. And then you'll know that the simple cubic real space lattice has a simple cubic reciprocal space lattice, but the lattice constant is 2 pi over A. All right? All right, so this might be a little bit difficult. I would encourage you to look at one of the solid-state physics books, whether that be Ashcroft or Merriman or Charles Cattell, solid-state physics books, to get a better handle on this. But basically, what this says is this. This is an example of looking at a BCC, body center cubic lattice, there in real space. This is where you may have zinc atoms here, 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 and here. If you then do this operation to get the B's, you will find that those B points, those reciprocal space lattice points have this configuration, which you realize, hey, these are face atoms here. So my BCC real space has associated with it this face center cubic lattice in reciprocal space. And that's what we're showing here. This BCC lattice has an associated reciprocal space lattice of an FCC, but with this lattice constant, 2 pi over A. But again, when I first learned this, I kept forgetting, when I was young, I kept forgetting what capital K is. It is always the incoming minus the outgoing wave vector. The sign doesn't matter here. We could add plus or minus this result. So you could flip this around, so it's Ks minus Ki. So what this whole analysis has been doing over the last 5 pages is finding the condition, finding the possible scattered wave directions. All right, we know that the magnitude of K sub s is equal to the magnitude of K sub I, but we never knew the direction of K sub s. And this analysis tells us that it must be the same direction as Ki. I mean, it must be Ki plus one of these capital K values, one of these reciprocal space translation vectors, capital Ks. All right, so this will end up giving us the scattered wave value, the incoming plus capital K. All right, so we're going to repeat that here below just to reinforce it. Thus, for any wave with K sub I incident on an array of scatterers, all right, and that could be a number of different things, the wave will only scatter with the scattered waves having K sub s that satisfies this result. So any waves that would have Ks being different than this will not exist in a crystal. It just will not exist in a crystal in that structure. So what this does is this prohibits any other wave that doesn't satisfy this result. All right. So finally we get, so that was some basic items. And we get to the final thing that we need for this, for moving forward. Because the very next lecture, we're going to use this result and use this result in the form of Floquet's theorem. And what this basically says is that this builds upon the result that we've developed over the last 16 pages, the last 5 pages especially, that all waves in a crystal have to have differences in their wave vector that are one of these capital K values. All right? So again, all the waves in a crystal must have a K value, an effective K value, whose only difference is that it is equal to K up to one of these K values. So this is your K effective for this particular component of the total field, and that this K effective must be equal to K, lowercase k, but adding one of these reciprocal space vectors, translation vectors. So this is going to be called Foucault modes, each one of these things. For if you have a simple cubic, you have particular values for capital K. If it's a BCC or FCC, you have different values. So we will show you how this is used in the next lecture when we look at simple diffraction gratings. And what we're going to do with the simple diffraction gratings in the next lecture is to analyze it in 2 ways. One way is using the RCWA algorithm, all right? And that you can think of that as a type of analytical method where we don't use any approximations, we don't do a grid like you would use in a finite element, a finite difference time domain, as you're going to do in the lab, but you're going to do a wave expansion, and that's why we need this Foucault's theorem, because we're going to express the wave as a linear combination of these Foucault modes. And for that, we needed to know how to expand it, and that expansion has to use this result right up here. And so we have to know how to get these K's, these reciprocal lattice translation vectors, and now you know how to do it. All right? So the next lecture is going to be on that, on looking at a periodic structure, namely an optical grating, and being able to expand the waves in the different layers according to Foucault's theorem, and then determining the reflection, transmission, diffraction, scattering from this periodic media. So if we were to go back and summarize this lecture, the overall thing we were learning is scattering of waves from periodic materials. And those materials could be a variety of different things, starting from the simplest optical gratings to photonic crystals, to irregular crystals, to plasmonic crystals, to anything with any periodicity. We then looked at some of the simplest behavior of periodic materials and looked at an incident wave impinging on a periodic array of wires. And we saw that there's a strict condition for the scattered waves such that all the scattered waves will constructively interfere. And we found that this condition must hold. And then we cast this condition in two different ways, either a very simple way that resulted in the diffraction grating equation, the diffraction equation, or a more general way that allowed for us to build up the concept of the combinational effects of an infinite array of scatterers, and what is necessary for a scattered wave to be present or not. And then we found that we needed to have this k dot r always being equal to an integer multiple of 2 pi. How do you get that? Your capital K's have to be of certain values. And then we calculated those values for the different types of crystals. For the simple cubic, for the body center cubic, and the face center cubic, we determined those K values have to be of this form right here. An integer times b1, an integer times b2 vector, an integer times b3 vector, with b1 vector, b2 vector, b3 vector being given by this. Those three things are in terms of the primitive real space translation vectors. Once we did that, we could get these primitive, these possible K values that we then put into this equation right here to get the possible scattered components. It was only these scattered components that can be present in the crystal, and that led us up to Foucault's theorem, saying that a wave in a material has to have K vectors that, with the difference between one wave's K vector and another wave's K vector, can only be have a difference of some multiplicative constant of one of these possible K values. One of these possible K values. All right, that's it. And I will be assigning a homework. Keep an eye out for that. I'll send out an email alert once I get that up, and take care. And I'll also schedule another help session in the coming couple of days. All right, bye.